Ladies and gentlemen, imagine a machine so massive, so precise that it can shape the future of transportation with a single press. A machine that can replace hundreds of parts with one, cutting complexity, cost, and time, forever changing how vehicles are made. This is not science fiction. This is the next leap in engineering, where speed, efficiency, and innovation collide to redefine what's possible. In the next few minutes, you will see how this monumental breakthrough is not just building cars. It's building a future where production, design, and technology move faster than ever before. The announcement that a 16,000-ton Giga Press is coming represents a decisive step in the ongoing effort to rethink how vehicles are engineered, manufactured, and scaled. From the earliest days, the focus has been on eliminating unnecessary complexity and replacing it with elegant, physics-driven solutions. Manufacturing is not treated as a background process but as a core product in itself, one that must evolve as quickly as the vehicles it produces. The move toward an even larger Giga Press reflects that philosophy at its most ambitious level. And a Giga Press of this scale is designed to transform how large structural components are made. Traditional automotive manufacturing relies on hundreds of individual stamped parts welded and bonded together over time. Each part adds cost, weight, tolerance, variation, and potential failure points. By contrast, a single ultra-large casting replaces dozens, or even hundreds of components with one integrated structure. A 16,000-ton press pushes this concept further, enabling the creation of larger, more complex castings with improved strength and consistency. This approach reduces the number of steps required on the factory floor and dramatically simplifies production lines. And at the heart of this strategy is the idea that the best part is no part. When parts are removed, problems disappear with them. Fewer robots are needed, fewer quality checks are required, and fewer supply chain dependencies exist. A larger press allows entire sections of a vehicle's body to be cast in one shot, aligning perfectly with the broader goal of building vehicles that are lighter, safer, and more efficient. The result is not only a reduction in manufacturing cost, but also a platform that is easier to scale globally. And the engineering challenge behind a 16,000-ton Giga Press is immense. It demands breakthroughs in materials science, thermal management, die design, and real-time process control. Molten aluminum alloys must flow precisely into massive molds, cool uniformly, and maintain structural integrity at a scale rarely seen in the automotive world. Advanced simulation software, AI-driven quality monitoring, and custom alloy formulations all play a role in making such a press viable for high-volume production. This is manufacturing treated with the same intensity and innovation typically reserved for product design. And the benefits extend beyond speed and cost. Large structural castings allow engineers to rethink vehicle architecture from the ground up. Battery packs can be integrated more directly into the structure, improving rigidity while reducing mass. Crash performance can be optimized through continuous load paths rather than assemblies of discrete parts. Dimensional accuracy improves because there are fewer joints and alignment steps. Over time, this leads to vehicles that feel more solid, respond more predictably, and deliver better efficiency per unit of energy consumed. And from a factory perspective, a 16,000-ton Giga Press supports the vision of highly automated, high-throughput production. Shorter production lines mean smaller factory footprints and faster ramp-up times. New factories can be brought online more quickly with fewer constraints imposed by traditional body-in-white processes. This flexibility is essential when the goal is to scale sustainable transport as fast as possible while maintaining consistent quality across continents. And there is also a strategic dimension to this development. By investing deeply in proprietary manufacturing technology, long-term advantages are created that are difficult to replicate quickly. It shifts competition away from surface-level features and toward fundamental efficiency and scale. When manufacturing innovation accelerates faster than industry norms, it becomes a multiplier for every future vehicle program, enabling rapid iteration and continuous improvement. And the 16,000-ton Giga Press is not simply a bigger machine. It represents a belief that the factory is the product. Every improvement in casting size, cycle time, and integration feeds directly into better vehicles and faster adoption of electric mobility. This relentless focus on first principles, combined with a willingness to take bold engineering risks, continues to redefine what is possible in modern automotive manufacturing, pushing the boundaries of scale, simplicity, and performance at the same time. And this shift toward unprecedented scale in casting also influences how teams think about iteration and learning. When a single casting replaces an entire subassembly, every design update carries more impact, but also more clarity. Feedback from the factory floor becomes easier to interpret because there are fewer variables obscuring the signal. If something improves, it is immediately visible in cycle time, scrap rates, or structural performance. If something fails, the root cause is easier to isolate. This tight feedback loop is essential for moving fast without sacrificing reliability. And a press of this magnitude also changes supplier relationships and raw material strategies. Instead of coordinating dozens of stamped components from multiple vendors, the focus narrows to alloy composition, die durability, and press uptime. This creates opportunities to co-develop materials specifically optimized for large structural castings, balancing strength, ductility, and recyclability. Closed-loop recycling becomes more practical at scale, with scrap aluminum fed back into the process and reused efficiently. Over time, this reduces both cost volatility and environmental impact, reinforcing the broader mission of sustainable manufacturing. And energy efficiency is another critical consideration. While a 16,000-ton Giga Press is an enormous machine, its net energy footprint per vehicle can be lower than traditional methods. Fewer machines running for fewer steps means less cumulative energy consumption across the production line. Shorter production cycles reduce the need for intermediate storage, transport, and rework. When factories are designed holistically with casting, battery production, and final assembly, tightly integrated, energy losses are minimized and throughput is maximized. And this approach also supports a more resilient production system. Simplified processes are inherently more robust under stress. With fewer parts and fewer handoffs, disruptions have less room to propagate. Whether dealing with supply chain fluctuations or rapid demand changes, a highly integrated casting-based architecture allows faster adjustments. Capacity can be added by replicating proven modules rather than redesigning entire factories. This modular scalability is essential when building millions of vehicles across diverse markets. And on the engineering side, large castings unlock new possibilities for digital manufacturing. High-fidelity simulations can model the entire structural component as a single entity, enabling optimization that would be impossible with fragmented assemblies. Machine learning systems can analyze sensor data from every shot of the press, predicting where, detecting anomalies, and continuously refining parameters. Over time, the press becomes smarter, more precise, and more reliable, turning manufacturing data into a competitive advantage. And there is also a human element to this evolution. While automation plays a central role, it elevates the kind of work people do rather than eliminating it. Engineers and technicians spend less time managing complexity and more time solving meaningful problems. Maintenance becomes more predictive, quality control more analytical, and process improvement more strategic. The factory becomes a place where software, hardware, and human insight converge, each reinforcing the other. And as vehicle programs evolve, the flexibility of large-scale casting supports faster platform changes. Instead of retooling hundreds of dies and welding fixtures, updates can be concentrated into fewer, more impactful components. This accelerates the pace of innovation and reduces the lag between design intent and production reality. When design and manufacturing are tightly coupled, bold ideas can move from simulation to the road with less friction. And the broader implication is a redefinition of what automotive excellence looks like. It is no longer just about horsepower, range, or acceleration, but about how efficiently those outcomes are achieved. Manufacturing efficiency becomes inseparable from product performance. A vehicle that is simpler to build with fewer parts and tighter tolerances tends to be quieter, stronger, and more durable. These qualities emerge naturally when the production system is designed from first principles rather than inherited conventions. And by pushing casting technology to the 16,000-ton level, the boundaries of industrial capability are being tested and expanded. This is not an incremental upgrade, but a statement that manufacturing can and should evolve as aggressively as software or electronics. Each leap in scale creates room for further simplification, deeper integration, and faster learning, reinforcing a virtuous cycle of improvement that spans design, production, and real-world performance. And this momentum toward ever greater integration naturally extends into how future vehicles are conceived from the earliest sketches. When engineering teams know that massive single-piece castings are available, design constraints shift. Instead of designing around the limitations of stamping and welding, structures can be shaped around optimal load paths, airflow, and packaging efficiency. This freedom allows vehicles to be designed more like cohesive systems, rather than collections of parts, improving both performance and longevity. And the implications for safety are significant. Continuous structures distribute forces more predictably during impacts, reducing stress concentrations that can arise at joints and welds. With fewer interfaces, there are fewer opportunities for variability to compromise crash performance. This consistency supports more accurate modeling and testing, allowing safety improvements to be validated digitally before physical prototypes are built. Over time, this accelerates safety innovation while maintaining strict real-world validation. And manufacturing speed is another area transformed by ultra-large casting. Cycle times measured in minutes replace processes that once took hours across multiple stations. As throughput increases, inventory buffers shrink, freeing up capital and floor space. This leaner operation aligns with the broader goal of building factories that are not only productive but adaptable. Lines can be rebalanced more quickly and production volumes adjusted with less disruption, supporting rapid responses to market demand. And the scale of a 16,000-ton press also encourages deeper vertical integration. When critical manufacturing steps are brought in-house, iteration becomes faster and intellectual property more secure. Software controlling the press, alloys flowing through it, and dies shaping the castings can all be optimized together. This holistic control enables refinements that would be difficult to coordinate across fragmented supply chains. The result is a tighter feedback loop between design, manufacturing, and field performance. And material innovation plays a central role in making such scale practical. Large castings require alloys that can flow smoothly, cool evenly, and maintain strength without excessive heat treatment. Continuous experimentation leads to formulations tailored specifically for structural components, balancing stiffness, crash energy absorption, and corrosion resistance. These materials are not static. They evolve alongside the manufacturing process, improving with each generation of vehicles. And sustainability remains embedded in this approach. Large-scale casting reduces waste by eliminating redundant material overlaps common in multi-part assemblies. Recycling streams become cleaner and more efficient when fewer alloy types are involved. When combined with renewable energy sources powering factories, the environmental footprint per vehicle continues to decline. This is sustainability achieved through engineering discipline rather than compromise. And the influence of this manufacturing philosophy extends beyond a single product line. Once a process proves itself at scale, it can be adapted across multiple platforms, from compact vehicles to larger utility formats. Shared casting architectures enable economies of scale, while still allowing differentiation where it matters. This balance between standardization and flexibility is essential for serving diverse markets without sacrificing efficiency. And data is the silent partner in this transformation. Every casting shot generates a wealth of information, from temperature gradients to pressure profiles. Analyzing this data in real time enables continuous refinement, catching issues before they manifest as defects. Over months and years, patterns emerge that inform design decisions, material choices, and maintenance schedules. Manufacturing becomes a learning system, improving not in steps but continuously. And as factories evolve around these capabilities, the distinction between product development and production blurs. Engineers consider manufacturability from the first concept, and manufacturing teams contribute to design decisions early. This collaboration shortens development cycles and reduces costly late-stage changes. When everyone works from the same set of first principles, progress accelerates naturally. And the pursuit of a 16,000-ton Giga Press reflects a broader conviction that scaling sustainable technology requires bold integrated solutions. It is an acknowledgement that incremental gains are not enough when the objective is global impact. By reimagining how vehicles are built at the most fundamental level, the path opens toward faster adoption, higher quality, and a manufacturing ecosystem capable of supporting the transition to a more efficient and electrified future. And this same mindset carries into how future factories are planned and constructed. When production revolves around a smaller number of highly capable machines, factory layouts become simpler and more intentional. Material flow is shorter and more direct, reducing internal logistics and the need for complex conveyor systems. Buildings can be designed around optimal workflows rather than inherited constraints, enabling faster construction and quicker commissioning. Each new facility becomes a refined version of the last, incorporating lessons learned and pushing efficiency further with every iteration. and the impact on quality consistency is profound. Large integrated castings reduce tolerance stack-ups that typically occur when many parts are joined together. Dimensional accuracy improves because alignment is no longer dependent on dozens of fixtures and weld points. This consistency translates directly into better fit and finish, quieter cabins, and improved long-term durability. Variations between vehicles shrink, allowing software calibration and mechanical tuning to be applied more precisely across an entire fleet. And this level of repeatability also supports faster global expansion. When manufacturing systems are standardized around a small number of core processes, they can be replicated more easily in different regions. A factory built on one continent can achieve similar output and quality to another with less ramp time. Training becomes more focused, spare parts inventories simpler, and operational best practices easier to transfer. Scale stops being a burden and becomes an advantage. And the role of software continues to grow as these machines increase in capability. Control systems manage thousands of variables in real time, adjusting parameters to maintain optimal conditions shot after shot. Predictive algorithms anticipate maintenance needs before failures occur, maximizing uptime and extending equipment life. Over time, the press becomes less of a static tool and more of an adaptive system, improving through data and experience, much like a living product. And this evolution influences how cost reductions are achieved. Instead of relying on supplier negotiations or incremental material savings, cost efficiency is designed into the process itself. Fewer parts mean fewer purchase orders, fewer inspections, and fewer opportunities for defects. Capital investment shifts toward high-impact equipment that pays dividends over millions of units. The economics favor long-term thinking, where upfront complexity yields sustained operational simplicity. And as vehicle architectures evolve, the integration enabled by massive castings allows for more creative packaging solutions. Space once consumed by overlapping structures and reinforcements can be reclaimed for passenger storage or energy systems. Lower mass improves efficiency, extending range without increasing battery size. Structural rigidity enhances handling and ride comfort, demonstrating how manufacturing decisions ripple through the entire user experience. And there is also a strategic resilience in owning and mastering such core technologies. When critical manufacturing capabilities are developed internally, dependence on external bottlenecks decreases. This autonomy enables faster responses to change, whether driven by new regulations, material availability, or customer demand. Innovation cycles shorten because experimentation is not constrained by long supplier lead times or legacy processes. And the cultural impact inside the organization is equally important. Ambitious manufacturing goals attract engineers and technicians who want to work on problems at the edge of what is possible. This concentration of talent accelerates learning and fuels a culture where challenging assumptions is encouraged. When teams see bold ideas translated into real working systems, confidence grows, and the appetite for further innovation increases. And looking forward, the lessons learned from operating a 16,000-ton Giga Press extend beyond vehicles. The same principles of integration, simplification, and scale can influence energy storage infrastructure and other industrial systems. Manufacturing becomes a platform for solving large problems efficiently rather than a constraint that limits ambition. And each advance reinforces a simple but powerful idea. Progress is fastest when products and factories are designed together. By treating manufacturing as a core technology, not an afterthought, it becomes possible to move faster, build better, and scale solutions that matter. The push toward ever larger, more capable casting systems is a visible expression of that belief, reshaping not only how vehicles are built, but how industrial innovation itself is approached.